Great. Well, welcome back for day 5 of our R tutorial. Rather than focus on programming per se, I really felt that it would be good to talk a little bit about statistics. I'm not going to go into anything advanced particularly on statistics today, but I felt that since most people use R for biostatistical analyses, sooner or later we were going to get around to some statistical testing, some hypothesis testing. So today I've made a relatively small amount of code that we're going to evaluate in a few different contexts as a way to evaluate how t-test performs in a lot of circumstances. I think most people here will have heard of t-test at some point, and it is by far the most frequently used of all statistical tests. So if I can if I can help you avoid making some invalid conclusions about the performance of t-test, I think that that would be time very well spent. So I'm hopeful that we can do that today. We'll start with a couple different versions of the same function here. You can see these at the top of the script for the code here. Let me see, I've got my R window's open behind it there. So we're going to start by looking at two different definitions of the same function. One of these reflects the way that R probably should be written, and the other one reflects a way that I think is a little easier to understand given what we've discussed already. So I would point you to our function is called Ttest Percent. Ttest Percent. Here we're creating a function that is going to ask us how many of these t-tests provided a significant p-value. Okay. Now in this case, I'm giving it some variables. We can give these as we call the function. One of these is an n, and one of these is a difference. Everyone see that? So by default, we're going to use the number 3. People very, very frequently will run a t-test of these 3 values versus those 3 values and ask, are they different or not? It's a pretty straightforward application of t-test, right? Why do we do experiments in triplicate so frequently? What's that? Accuracy. Okay, I think what you're alluding to is there's some variation that always creeps into our experiments, and we need to characterize the variation. That's correct. So if you just did an experiment once, would you know how stable that measurement is? Not really. And one of the factors that we must have in order to compute the t-statistic is how much variability was seen. So yes, because the numbers dance around on us a little bit and we want to characterize how much they dance around, running a test in replicates, running it 3 times, for example, is helpful for us to characterize that variability. Okay, that's one place. Anyone else have a reason why we do 3? Third time's the charm. Okay, so some might argue that if you did the experiment once, you'd have no idea of variability. If you did it twice, you would have 2 values, but you wouldn't really know variability well. I mean, one of those numbers could be quite reflective of the true number, and the other one might be off. You wouldn't know which. Doing it 3 times is lucky. Okay, so this is not far from how people think. So I think it's a good thing to say. Anyone have another reason? Is it possible to do t-test with just 2 replicates? Anyone know? We can check. We'll just pop over here to our R window, and we're going to type in t-test. And now I'm going to give it 2 vectors of numbers. I'm going to make one 1.5, 1.8. And now I'm going to give it another vector, and this one's 1.6, 1.7. Remember, you have to close out the second pair of parentheses as well. Well, how about that? We didn't, after all, need 3 replicates in order to run t-test. So you can do this with just 2 values on either side. So we might say then that doing it in triplicate means getting enough to pin down variability a bit. I would state that one of the big challenges that we most frequently run into with t-test is that it really kind of struggles to deal with whether the variability has been, whether the variance has been accurately estimated from these samples. Okay, so these are questions I want you to think about as we move ahead today. All right, so I'm going to enter this code into R so that I have my function available to me, my Ttest percent. So let's walk through what happens within this code. I've already mentioned that we're going to be examining two cohorts, a bunch of A values and a bunch of B values. I'm going to have 3 values within each of those cohorts, but you'll see that I'm actually doing 100 different t-tests with those, with that number of replicates and that difference between means. What should be the behavior of t-test? If you're testing for a significant difference between an A cohort and a B cohort, and there is no difference, what should the p-value that returns from t-test be? There's no difference between cohort A and B. What p-values should respond from t-test? Nothing? It's going to give you some number back, right? What is a p-value allowed to range over? 0 is the smallest. Well, you couldn't get to a 0 per se, but you could get close to a 0 on one end. And on the high end, you could get to 1. All right. So I'm going to run the guts of this code, providing these numbers n equals 3 and diff equals 0. Okay, so n equals 3, diff equals 0. And now I'm going to just run the guts of it. Okay, down to there. I'm going to run everything after the function definition. Remember that those variables inside there will not be accessible to us when we run the function. The function will compute them and give us a return value, but it won't show us what its work is. So I'm going to grab out the insides and paste that right here. All right. So we are collecting, we're putting together these matrices of numbers. Let's look at what those look like. Random A's, I have 100 rows of them and 3 columns of them, because we're going to do 100 different t-tests, 100 sets of A's versus 100 sets of B's. All right, and we see that we have the same size for the random B's, 103. So this function right here, cbind, if you remember, will pull in this set of this matrix and that matrix and bind them in side by side. It's a column bind. If we had rbind, it would stick one after the other. Instead, we're going to stick them in side by side. So if we look at the randoms that were pasted together, we see that we have still 100 rows and 6 columns. Everyone doing okay so far? Okay. These are all just random numbers that have been put together. The difference in mean is 0 between these. From the distributions that were used to produce these random numbers, they have exactly the same mean. All right. Now, this next line should puzzle you, I think. Apply, in my view, is one of the most difficult to understand commands that we find in R, and yet it is one of the most powerful. Remember that I said apply should give you the ability, that one of the superpowers of R is its ability to do the same operation again and again very, very quickly. Apply is one of the major gateways for accomplishing that. So the apply here is written in such a way as to grab out each row of this 100-row, 6-column table, and for each row, compute the t-test of the first 3 values against the last 3 values, and then store that p-value in a vector called p-vals. Now, I think that that's a little hard to get from looking at these lines. So I'm going to ask you instead to look down here. These lines will accomplish exactly the same function, but in theory, the apply version should run a little bit faster. In my view, one of the things that most holds back people from from coding well is not being able to understand what's been written. So even though the apply version runs very slightly faster, I actually think the for version, although it is also longer, is actually easier to interpret. So let's look bit by bit how this goes. So we're going to start by creating a vector called p-vals, and it has 100 rows, and every one of those is a not applicable. Everyone sees that? So to start, this is just it's just a NA, all the way down 100 rows. And now we're going to count through the number of rows, which you remember is 100. We're going to perform 100 t-tests every time this runs. And here we're going to set the value for row number 1, when we're sitting on row 1, with the p-value that results that results from a t-test of the first 3 values versus the second 3 values. Here I'm grabbing them from randoms A and randoms B rather than out of the big table, but the effect is exactly the same. So the t-test returns a list, and one of the values within that list is a p-value. We can look at that a little more slowly. If I do I'm going to call my test equals t.test of C1, 2, 3 versus C4, 5, 6. There. Right, this is a t-test where I'm comparing the values 1, 2, and 3 to 4, 5, and 6. The values don't really matter here. Okay, so what we can recall is that my test has a structure to it. We see that the value returned by t-test is a list that includes a statistic. This is the t-statistic that the t-test is named for. It has parameters, including the number of the degrees of freedom. It has a p-value, a confidence interval, an estimate, a null value, and the alternative hypothesis, etc. So the t-test is returning this complex object, and from it, we're going to extract just one thing, just the p-value. So if we look at my test by itself, we get back this pretty printed version of all those values, but we can grab out just the p-value like that. Everyone see that? I see some frowns.
So what's STR?
Oh, STR is a structure. When you have a complex data structure, it can tell you what the insides of it are. So my test was what returned from the t-test, and when I ran a structure on my test, it showed the guts of it. Basically, what are the named elements of the list that comes back. Okay, so when I looked at my test $p.value, I was able to pull just the p-value out of that structure returned by the t-test. We talked about lists on the first day. We've been thinking about lists like data frames, where we have vectors of the same length that have all been grouped together as a data frame. A list is frequently used for functions returning a complex product, like a t-test. Okay, so to return to this code, for each row of these 100 values, we're going to perform a t-test. We're going to grab the p-value from that test and jam it into this array of p-values that we had created. I think that this is a little easier to understand than the apply language above it, because this unfolds it into how the orderings in which this was generated, makes it very clear that we're grabbing these values to be compared to those values and so on. It's a little more explicit way to tell the story. But the two functions, when run, give exactly the same result. Okay, so let us now run Ttest Percent by itself. You're just going to get back an integer. I'm going to run it a few times. Okay, so because I've run it by default, with all the default options in place, what is the true difference in the means between the A values and the B values, between our two cohorts? If we flip back to the code, we see that the difference by default is set to 0. So there's no difference to be found here. The A values are drawn from the same distribution as the B values are. But what is this? Why is this t-test percent giving us positive values? What does that mean? Well, we see that the number of significant values here is running a subset. Remember, we had created this big p-vals vector that has 100 different p-values in it. Now we're running a subset on it. Let me see. I'll call it p-sub. P-sub is going to be the subset of the p-vals such that p-vals greater than less than 0.05. I believe that's what I had written in my code. So if I just say p-sub, I can see that I don't have 100 values anymore. I only have the ones that were less than 0.05. A lot of this is using functions and programming strategies that we've talked about through this week. So I hope that this doesn't come across as complete mysticism. Is it mostly making sense? The only truly new thing we've seen today, well, maybe structure was new. I'd forgotten. I maybe didn't introduce that one. But this business with apply is the only thing I'm trying to do really differently in coding today. So the apply can be written this way, and if you're a great programmer, perhaps that's a more efficient way for you to remember how to do things. But personally, I find that using this structure makes it a whole lot easier to understand what that function is doing rather than using apply. All right. So in the case of the software, the value it's returning is not p-sub, as we've called it here. It's instead saying, what is the length of p-sub? I saw a frown back there, so I'm going to try to be careful on this. Every time I see a frown, I'm like, I don't want to lose people. I want them to understand what's happening. All right, so this might seem like just a whole lot of polishing, and it may not be clear where we're going with this. So I want to explain a very important principle just from the word go. T-test can tell you that you've got a significant difference when no significant difference exists. Did everyone get that? That is a really important take-home for today. P-value can give you a significant result even if the two sets of values are drawn from the same distribution. Okay, so I'm talking a lot about normal distribution today. I want to take a moment to draw some pictures because I think that may help illustrate things. So I'm going to drop down here and run this block of code. We'll be coming back to the t-test here shortly. All right, I've drawn a picture using one new function here. We'll just look at it. So we've talked before about the series operator. If you say 1:10, what does that evaluate to? 1:10, does anyone remember? I'll just come down here and type it. I'm okay with that. 1 to 10. All right, so 1:10 can give us back a whole series of integers particularly, or a series of letters for that matter. In this case, I've used this call to sequence. You see sequence there? This is not like a biological sequence though. This is a sequence of numbers that run from a minimum to a maximum with some step size. The step size in this case is going to stop every 1,000th of the distance from -4 to +4. So if I run just that line, I see that I can play back those values, and there are 1,000 of them. All right, so if I do a quick length on x, you'll see it's 1,000. The line that we ran was this one to produce that. So its value, it's just as the sequence operator, the colon symbol, gives us a series of integers. This can help us to divvy up a space, a specified range, into some number of bins. In this case, we've set it to 1,000. All right. For the next line of the code, I used dnorm. Now you've seen me use rnorm before. In this case, though, I'm asking it, what is the probability under the normal distribution to get this value from the normal distribution? So rnorm, if I said rnorm 1,000, is going to give me back 1,000 random numbers from a normal distribution. In this case, I've told it, tell me exactly the probability of this set of outcomes, that set of outcomes, that set of outcomes. And then I'm going to plot them in a line graph. That's what this plot x hk type L means. So we are creating a scatter plot, although it doesn't look like one. We're creating a scatter plot where x is this location between -4 and +4. Our y-coordinate is going to be the height at x. And then type equals L says this isn't just an ordinary scatter plot where I want a bunch of circles. I want these points all to be connected by lines. Something not making sense. I saw a head shake there.
That was nothing.
It was nothing? Was it a good joke?
No, nothing.
I love good jokes. All right, that's fine. We'll move on with it. Okay, so after that, you can see that I've used a bunch of AB lines. These AB lines are what add the horizontal and vertical lines to the graph that we saw for just a brief moment there. So you can see that I've colored the one at 0, which is the mean of this distribution. I colored that in purple. And then I put in 2 more lines at 1s, those are in red, and 2 more lines at 2. Well, 2 and -2, those are in blue. So let's return to this graph that we've produced. Here is our example of the normal distribution, not from sampling, but from the height along this curve all along there. So we didn't provide any parameters to dnorm when we ran it, which means that it's going to default to its standard values, which would be the mean is at 0 and the standard deviation is at 1. So we want to explore what that means. So first off, does the normal distribution extend beyond 4 and -4? I hear a no. The normal distribution goes on infinitely. So you'll get a positive value even if you feed this normal distribution the value 1,000,000. It'll still be giving you a non-zero value, but it's very, very close to 0. So that's an important starting place. The normal distribution is going to give you this mean of 0, and it's going to have a standard deviation of 1, but it never actually hits 0 on its flanks. It's just very, very small. But let's talk about where the bulk of that information is, where the bulk of the area under this curve can be found. So the typical rule that we use is that if you have a normal distribution, I believe 68%, do I have the number straight in my head? 68% should fall within 1 standard deviation. By default, because we didn't tell it what standard deviation to use, it's going to give us back a standard deviation of 1. So if you look at the 2 red lines, they are a depiction of what plus or minus 1 standard deviation means in this normal distribution. 68% of the values that come from this normal distribution should fall between those red lines. We also have lines drawn at plus or minus 2. That represents 2 standard deviations out. So if you have just under 70% between the red lines, you should have just under 95%, or is it just more than 95%? A little bit more than 95%? You should have around 95% between the blue lines. Does that hold up? Does that look like about 95% of all that area? It's about right. About 95% of the area falls between those blue lines. Now, I didn't draw in lines at plus or minus 3. I could do that. If I were to do that, I would have accounted for 99% of the values that come from this distribution. So we have this smear, the further you get away from the mean, the less likely an outcome it is that a sampled value will fall in that space. Okay, so now that we're all reminded of the normal distribution, I'm going to try to bring in a visual of the kind of tests we're doing today. Because we're not comparing a bunch of values with no difference, typically, in a t-test. If we knew they had no difference, we wouldn't be doing difference testing. But instead, we're comparing values between two cohorts. So I want you to think about how much difference there is between the means when we look for differences. This is what it looks like when there's no difference between the means of A and B. The A values come from exactly the same shapes than the B values do. However, you might instead have a plot like this one. Now we're going to shift to using black and red to represent our two cohorts. So I'm going to copy this next section in. All right. So something has changed, right? We now have two normal distributions because they're distinguished from each other. The black one and the red one are separated from each other. How different are the means of these two distributions? The mean of the distribution is indicated by what? The line, the vertical line. So how different are the two means here? 1. Yeah, that's it exactly. Right. The legend here doesn't show us a mark at 1, but the red mean is 1 unit higher than the red mean. Okay, so the point I want to illustrate is that the further apart the means are between your distributions, the better your chance of spotting that they are different. Obviously, if there's no mean between them, there's no difference to be found. In this case, you could have, we're talking about a difference of 1 standard deviation between one cohort and the other cohort. So this is a true difference that exists, but if you were to randomly choose values from the reds and randomly choose values from the black, would it always be possible that t-test would tell them apart? No, frequently it would fail to find a difference of this magnitude. The other factor I want you to think about is the number of replicates. If you had 1,000 values from red and 1,000 values from black, do you think you could tell that they were from different distributions? Well, if you're using t-test on the values that came back, could t-test tell 1,000 reds from 1,000 blacks apart? Very confidently, very, very confidently, every time t-test is going to tell you, oh yeah, those are different, they're totally different. But if you have just 3 values, your ability to tell these apart is going to be much more limited. All right, I'm going to do one more plot. It's the next one right beneath that. This time, we're shifting to a pretty large magnitude difference. Okay. Now you see that the red mean has moved all the way up to 2. So we see that black and red are not baseline resolvable. I mean, that's the way we talk about it in mass spectrometry. But if you have 3 values from red and 3 values from black, you've got some shot of finding the difference. The greater the difference between means, the easier it is to spot a difference. The more narrowly spread the two cohorts are, the lower the standard deviations for them, the easier it is to spot a difference. The more replicates you've got, the easier it is to spot a difference. So when you design an experiment, I want you to think about how big an effect am I looking for. If it's a very small shift in the mean, you're going to need more replicates to go after it. You need to think about how noisy is the experiment I'm performing. If it's very variable, if it has a high variance to it, you're going to need more replicates to go after it. All right, The other thing that you should think about, we've already talked about the problems of finding money to pay for bursaries. There's also the money to pay for experiments. How much money does it cost to sequence something these days? We recently paid for 6 RNA-seq experiments over at CPGR, so 6 different samples to get sequenced. It cost us about 50,000 Rand. What's a bursary for honor students? 20? 30? Do they give you 100K a year? Your fees are 35. Okay, that's good. That's a fine reference point. So if it costs 35,000 Rand a year to do honors education, you could spend that. We'll be very loose about it and say you could either pay 2 honor students to be in your lab this year, or you could pay for one of these RNA sequencing experiments that we did. Okay? So if I were doing variation, if I were trying to do measurements and I was trying to find a difference in RNA-seq, I would want to pay for as many replicates as I could. Since I did 6 experiments, I could have done 3 replicates of A and 3 replicates of B in my sequencing experiment for the price of 2 honor students in one year. It's expensive, right? So the number of N that I can achieve is going to be a little problematic here, because I know I'm going to have to pay for a higher N, a higher number of replicates. So science is real. I mean, we need to think about real things. So one of the things I could hope to do is go after differences that are big in order to look for larger mean differences, thus making it more likely I could find a difference. Or I need to go for methods that produce low variability, because paying for 100 samples to be sequenced is well outside my budget. Okay, that's the kind of calculus we always need to think about when we're performing these experiments. I tend to call this the 4-legged stool when I'm giving my lecture about it, because it's a talk about power. How can you design an experiment that is likely to give you a useful answer about the phenomenon you're trying to observe? It depends how big a difference that exists. It depends how much variability you have on the sample cohorts you're examining. And it depends how many N you can afford. That's just 3 of the stools. That's fine. Okay, so this picture that I've been showing you of no difference between means, 1 standard deviation between means, and 2 standard deviations between means is intended to make you think about just how big a difference is available to be observed. Great. Now, I want to return now to our big question. If we perform 100 t-tests, these are Welch t-tests, with 3 replicates and 2 cohorts that are from distributions with the same mean, how many would be called significant differences? And here's the other part, even though we know there's no difference to be found. So I can grab out this line of text and I can run it several times. I'm going to shift now to vertical tiling so we can see those. Looks a little different when it's squished this way rather than that, right? Okay, so I'm now going to run Ttest Percent enough times to just give us something to look at on screen. All right, I've now run it several times. You can see that each time I achieved at least 1 t-test that provided a significant p-value. Every time I had at least one of these tests giving me a significant p-value. So let's put that in the context of your experiments. Sometimes, if you do 100 t-tests in your experiment and there's no difference to be found, t-test will still tell you that there's a significant result. That is an important cautionary tale. If you do t-test on a whole pile of different statistics that have no differences, it will still find sometimes real significant differences exist. So let's return to the concept of p-value. The p-value is what we harvested out of the t-test. And p-value is very frequently what people say constitutes some sort of ironclad guarantee that if a difference exists, it's going to give you a value below 0.05. But that really means they have no idea what p-values represent from t-test. So what I want you to remember is that t-test is testing the null hypothesis. It's saying that if there were no real difference in the means between these cohorts, what fraction of a time would I see a result this dramatically different? The way to interpret a p-value of 0.05 is to say that 5% of the time I would expect to get a result this extreme even if there were no significant difference. We've just run a whole bunch of tests of that. And we see that the results fall pretty much in line with that. In this first example on screen, 4 of our 100 tests had significant p-values when we did 100 of them. We expect 5% of t-tests when there's no difference to give a p-value of 0.05. Okay, so we see that 4 of them, 3 of them, 2 of them, 4 of them, 6 of them, 1 of them, 2 of them, 3 of them, 5 of them gave us significant p-values even when no difference was visible. That is an important cautionary tale because you can get a significant p-value when there's no difference. Everyone has that. Great. Let's move on to the next part of this then. For this next set, we are going to put in a small difference. Everyone remembers when the red and black curves first appeared. They were close together. So this represents a kind of hard place to spot a difference between the red and black or the A and B cohorts. So we're now going to run this block where our n is still 3. We're doing a triplicate experiment, but we have a relatively small difference between the cohorts. All right, I'm going to get myself a few blank lines and then hit away. All right, so there really is a difference between these cohorts, but did t-test find it for us? Did it say, oh yeah, they're different, they're totally different? Not consistently, did it? I see a 9 at 18% of the time, 7% of the time, 12% of the time, 15, 19, 16, 12, 11, 8. This is a tough difference in order to find, to recognize that there's a real difference on the basis of 3 numbers from red and 3 numbers from black. So that was not so great. Does it help if we instead provide a quintuplicate experiment? 5 values from red, 5 values from black. I'm going to go ahead and type this in. Did the numbers get better? Okay, so there's a real difference to be found. This is the one that we illustrated over here at the right. A difference of 2 standard deviations. We're grabbing 5 red numbers and 5 black numbers. Can t-test tell them apart? And we see that roughly somewhere between 1/4 and 1/3 of the time, t-test did find a difference. When you're going after some sort of biological difference, it's really valuable to know just how big a difference it should incur. If you're claiming that via qPCR, we should see that expression of this gene jumps by an order of magnitude between my 2 cohorts, that's a lot easier to go after than if you have a difference that's maybe a 20% increase in expression. Does everyone see that? Detecting a difference between, say, 5 versus 4, or 6 versus 5, I guess, rather than between 10 and 1, is quite different. The number of replicates you're going to need to go after it is going to be different. Okay, so we saw then that moving from a triplicate design to a quintuplicate design, 5 replicates rather than 3, increased the amount of time that we could spot a difference. Everyone sees that. So if your advisor comes to you and says, we're going to do 3 replicates in this cohort and 3 replicates in that cohort, what's your correct response? The correct response. It's such an arch thing to say. You could say, gosh, are we going to spot a difference if we use only 3 replicates? Is it possible for us to do 5? You can ask that question, and your advisor should have an educated response to that to your request. He or she may say, gosh, these experiments are so expensive we can only afford 3. And your response to that should be, okay, I'll help you write the next grant, but for now let's see what we can do. I'm just saying. Okay, so if you're looking for a big difference, you can probably get away with fewer replicates. But if you're looking for a very minor difference, a lot harder, a lot harder. Okay, this time we're going to go to a big difference. Now we have a standard deviation difference of a mean difference of 2. The mean for black is 0, the mean for red is 2. So we're now in this scenario where we're trying to find differences using 3 replicates. So I'm going to copy this section in here. There we go. How often are 3 replicates working to recognize differences? Somewhere between 1/3 and 40% of the time? Something like that? Okay, really important thing to recognize here. You may have a 2 standard deviation difference between your means and still not see it, even if you do 3 replicates. Imagine that you have 3 graduate students and each of them has been given a differentiation task of similar magnitude. In this case, one of the students, by random chance, is able to come up with a significant p-value at the end, and the other 2 are like, nope, wasn't significant. That's the reality. If you have a relatively small difference and not enough replicates to go after it, your chances of successfully recognizing the difference has fallen quite a lot. And now I'm going to come down to our final example. We now have a mean difference of 2 standard deviations, and we're going after it with 5 replicates. We generally fell below 40% with 3 replicates. How'd we do with 5? Well, look at that. Bloomed up to almost 80%, nearly doubled our chance of detecting the difference for real just by going to 5 replicates rather than 3. Okay, I hope that this has been useful in helping you think about what can come out of your research. There is a widespread perception that you have to do 3 replicates, otherwise you can't use t-test. And so a lot of people say, well, 3 must be enough as well. The smaller the difference you're going after, the more likely it is you're going to need more than 3 replicates. 5 replicates have a lot more power than do 3 in the same scenario. So the smaller the mean difference, the wider the variability, and the lower the number of replicates you do, the less likely it is that you come away with a significant difference in the end. However, also beware of false negatives and false positives. We've been talking about false negatives, where we have a true difference that exists in our samples, but our experiment wasn't good enough to spot that difference. That's a false negative. The opposite of this is that you may have no real difference. You run a t-test on lots and lots of different phenomena that have no difference, and one of them produces a p-value, and you then go chasing after it for another 2 years when it wasn't a real difference to begin with. That's a false positive scenario, and it's one that should scare you a lot. We use t-test for lots of things, but it's really important to remember that it is possible to get a false negative from it, and it is possible to get a false positive from it. So you may be dealing in a situation where t-test is not, in fact, the correct test to be using. I'm not even spending time on that because this isn't a biostatistics course. But there are people around here who can help you to realize whether or not you're using the right analysis for the situation that you're facing. And I hope that you will use their expertise. Okay, so that is our brief, scary look at T-Test. I hope that it will help you to be a better informed user of it and to protect yourself from some of its weirdness. Okay? Great. Thank you, everybody.